Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, and thank you for watching IT Pro TV, empowering the world through engaging learning. I'm your host, Zach Memis, as we continue on with compTIA Net Plus. Switching Technologies is the name of this episode, and Wes Bryant is here to help us out because he's a great guy. Wes, nice to see you, sir.
Hey, telling all those lies about me again. That's right, Zach. Thanks for having me back. It's always good to be here with IT Pro TV. That is right. We are moving through, if you're following along with us out there, we're moving through the Objective 1.3, which is routing and switching. And in this episode, we're going to be looking at some of the switching technologies that you need to be aware of when you sit that exam. Now, we're going to talk about some of the basics as well. We need to know things like, how do switches make decisions, and what is some of the information that's stored within them, as well as defining some of the basic concepts that can get a little bit confusing if you've never seen some of these before. So if it's the first time you're getting into Net Plus, maybe first time you're getting into networks, these will be some fundamental technologies that you're going to need to be aware of. And again, not just for the exam, but as you launch into your networking career.
And Wes, some of the episodes we've actually worked on together, you've mentioned packet switched and circuits. So what's the difference? I guess that's what we're leading into.
Hey, absolutely. That's a great concept. One of the most prevalent ways that we move information across networks is through what is known as a packet switching technology. In fact, our switches that we talk about, they work with data packets. Now, it's kind of interesting that we call it packet switched network, right? And when we talk about IP, that's technically where our packets, right? We talked about protocol data units, right? And IP, the IP layer, if you will, or internet layer, network layer, is where we have packets. But then when we talk about switches, we always talk about the fact that, well, switches deal with frames, they don't deal with packets. So what the heck is it that we mean? So in this context, when we talk about packet switch networks, what we mean is that it's a unit of measurement, if you will. A packet is a variable length size. It can change the lengths. And one of the things that's great about packet switching networks is that the way they have it set up is that packets can take different routes across networks to find their ways to the endpoints. And that's great. And in some of the earlier implementations of this, it's kind of like a military thing where they wanted, during wartime and stuff, portions of a network that could, unfortunately, be destroyed, right? And they wanted a way that these packets could be basically routed around the failed network and still make their way to the endpoint. So with a packet switching network, a couple of the characteristics that I want you to be aware of is that the packets are variable length. Right? There isn't any predictability, right? We have other different technologies out there like cell switching networks for the asynchronous transfer mode ATM, right? And that ATM, if you will, it uses these cells that are 53 bytes in size, and if your data isn't 53 bytes, well, guess what? You have some padding on there. We're going to make sure. The technology is, not us, but the technology is going to make sure that it's always 53 bytes that traverses the wire within those networks. So that offers a predictability, and we don't really have to calculate things like, the cyclic redundancy checks and stuff, so it's less prone to errors. But it's also more expensive technology. And Ethernet, when we talk about Ethernet, right, that's essentially packet switching type communication. Now, the other thing to keep in mind, too, is that packets will take different routes. They don't take the same dedicated path. They don't have a dedicated path, if you will. The connectivity devices will check some information, and they'll determine where that information needs to go and send it along its way. And then, even in the same data stream, you could have another, multiple packets that are taking different routes. And that's a little bit different than the circuit switching networks. Now, you mentioned circuits, right? Yep. Well, we also have circuit switching networks, and circuit switching networks, honestly, are some of the oldest network communications that we have. It's really one of the reasons you and I were talking about it at some point off camera before the episode. We talked about why was computing even really started, right? Why do we use binary? Well, if you go back into some of the earliest days when they decided, hey, that we need a way to control these circuits, these logical gates, if you will, and binary was perfect because what you would have in circuit switching networks, you probably remember some of the old black and white commercials where you had the ladies in there. And
I was just going to say, like operators at a switchboard.
That's right. They were our connectivity devices, right? If you look back, going back 100 years or so, those were our connectivity devices, right? They would receive a signal on one and say, hey, let me go ahead and connect you. Now, I want you to keep that in mind. The reason I use that analogy is because what were they doing? They were establishing a dedicated communication path, and that's what's a little bit different with circuit switching. See, with circuit switching networks like your PSTN lines, the public telephone switch network, the other, sometimes they call it POTS lines, you have a dedicated connection, right? When you make a communication across the circuit switch network, what you have is you have a circuit that is brought online, and it is a dedicated pathway between source and destination, and that portion of that network resource is actually temporarily used and other people can't use it, right? So it's a little bit different than packet switching where you could have one data stream that goes across the wire taking different routes. Circuit switching network, you build a dedicated point-to-point communication between the endpoints. Now I say point-to-point, it doesn't have to be a physical. They also have logical virtual circuits too. But keep in mind that with a circuit switching network, you have a dedicated path in between source and destination, unlike the packet switching network. So circuit switching networks are still out there as well. Again, that's what you have. Things like dial-up is a circuit switch type network. You have, for instance, again, those PSTN lines too. So that's a little bit, about packet switching networks versus circuit switching networks. I went ahead and just mentioned the other one, cell switching network, even though it's not really relevant to our content here. It is relevant to understand the three different types. Remember, cell switching network is a fixed length and it's predictable, right? Predictability means we know exactly what to expect every time, less error correction. Now, one of the great things about packet switching network is that if there are errors, and errors do are present, well, we just discard the packet and we do a request for retransmission depending on if we're using connection-oriented services or if we're using connection-less services. If it's connection-less services, we just throw the packet away and that's it, right? Goes off into electrical limbo. All right, so that'll move us into some of the other topics that we need to discuss. One of the things that I want to start out with is, and we've kind of talked about this in other episodes, is how do switches, right? How do switches make decisions on where to send information when they are communicating? Well, they do that with something known as a MAC table. All right, that's how switches communicate. And we talked about switches, the switch communication in an earlier episode. But I do want you to kind of understand, and that the MAC table essentially is a set of MAC addresses related to the ports that that devices are on. And when a frame comes into the switch, you have inside of that switch, you have basically a database that it's built up. And again, it is a port to MAC address mapping. So if I have a communication that comes in on port 1, well, the switch looks and it says, okay, what's the destination MAC address? Where is this supposed to be going? And it looks at that destination MAC address and then compares it to its MAC table and says, oh, okay, I see, just figuratively speaking, that this computer with this destination MAC address, let's say, is on port 22, and it forwards that information appropriately. Now, I want you to remember that when it comes to switches, not only do they have MAC tables, but just like our computers, they also have ARP tables too. And the ARP table, remember, is an IP address mapped to its MAC address. In fact, we've kind of looked at this before. I've got our Windows 10 machine here, and if you want to see, like on a computer, what the MAC table looks like, all you have to do is drop down to your command prompt, and you can do an ARP, right? If you run ARP by itself, it's just going to say, hey, you needed to have some kind of parameter option assigned to it, and you can see that we've got a few different options here. Let me go ahead and clear the screen, and we're going to do our ARP -A. And what that does is it shows us the ARP table that this computer has. Now, switches do the same exact thing. They have ARP tables too, and again, that's just your IP addresses mapped to your MAC addresses. Remember that your switch is making a communication or delivering or forwarding information based on that MAC address. All right, or the MAC address. All right, so know a little bit about the ARP table and what it is. You know what would be in there, as well as your MAC table too. All right, some of the other concepts that we need to look at, all right? So one of the things that they talk about are how do you control who or what devices can communicate and how and where they communicate. Well, that's through something known as an ACL. Just like in Windows, those of you that are coming over from A+, probably have heard about permissions, right? And I could say, okay, Zach, you are our IT manager. I want you to have full control over this file or folder, right? And that means Zach has a certain level of things that he can do over that file or folder. Well, believe it or not, you have access control lists inside of your switches as well. And switches, you can control how the traffic and who can communicate, what devices can communicate, through access control lists. So understand that an ACL is just a way to, an access control method that allows an administrator to configure the switch, put rules in there, and dictate how traffic can move, where it can move inside of the switch. Now, those of you that are going on to more advanced technologies or training, if you will, might get into the Cisco world where they're going to show you how to, inspect an ACL and do the configurations. But just know that an access control list inside of a switch really isn't much different in a concept as it would be like permissions inside of your operating system, like in Windows. Or if you look at firewalls, firewalls do what? They use a series of rules that either allows or denies traffic going in and out of an interface. Well, your ports are interfaces on switches as well, and you use ACLs to control who can communicate and who cannot communicate on on the switch itself. So that is something to keep in mind. Some of the other things that you need to be aware of too that they call out things like, for instance, port mirroring. All right, now port mirroring. Why would we do port mirroring? All right, well, I got a little diagram here, and I want to kind of show you what I mean here. So imagine, and these numbers, by the way, these port numbers, I just kind of randomly threw them out there. All right, so they're arbitrary. Just imagine that we got like a 48 port switch, and we've got a couple of devices that are connected to it that are in question here. Now, port mirroring is a great way that you can see the traffic. You can duplicate traffic that's going into one port on another port. Now, why might I do this? Well, you can do it for a few reasons, right? So notice that the source of the communication here and the destination, all right? And I want you to keep in mind that we also have a management station here too, all right? And when we look at this, notice that the source computer sends information into port 2, and the switch looks at its MAC table and says, okay, I see the destination MAC address is bound for this server here in this case, and that is on port 22. Let me send it out that port. But what's interesting is when you do a port mirroring, what you're saying is that this computer, let's say we're going to mirror port 2 with port 10. Now what happens is, even though the source of the communication and the destination of the communication are actually talking, all the traffic that goes in and out of port 2 is now going to be also duplicated over to port 10. Now, like I said, why would we do something like that? We can do it for a couple of different reasons, right? One of the reasons you can do it is for security purposes. Maybe you're doing some kind of security auditing. Maybe you've got an administrative station that you just want to see what they're doing, right? Maybe you've got something, somebody on your network that, again, it doesn't always have to be bad, right? That you want to just kind of audit what it is that they're doing, while they're at work. I'm not sure, but you can inspect and grab that information. So you can also do it as a way to just basically kind of like sniff traffic without having to have a protocol analyzer. But you can also do it for diagnostic purposes too. Maybe you want to see, a certain, for instance, if the roles were reversed and this server was what you were port mirroring, maybe you want to see the traffic that's coming in and out of the server so you can get a better understanding of the utilization of that server, maybe the overutilization of that server. Maybe you have to beef up the network adapter. Maybe 1 gig link isn't good enough. You need a 10 gig link. So again, you can do it for the purposes of just inspecting and diagnosing the information. We can also do this with things like IDSs too, intrusion detection systems. So it's really up to you. Just understand basically for the exam that port mirroring is a way that you can map traffic across or duplicate the traffic across ports, right? We could do it for, again, diagnostic purposes, auditing purposes, if we're logging information that's coming to and from a server. And again, we want to get some idea of what information, what is being sent in and out of that server. We can do that as well. So it's a good, handy thing to have. All right, so that's port mirroring. That's some of the properties of the interface, if you will. But there's also other things that you can do too. For instance, one of the things that we can do is something known as port security. Now, port security is a way that we can define exactly who, or I say who, but it's not us as the humans. It's the device, if you will, the node. I know I keep saying who can communicate, but what devices can communicate on a single port, right? So for security, imagine that, port security, but for security purposes, we want to ensure that somebody can't just randomly plug into a port and send their communications, right? Now, physical security is one of your second lines of defense, only preceded by policies, procedure, and awareness, but we do need physical security. So port security is a good way that physically you can say, hey, I'm gonna only allow this computer to send information into that port. All right, so let's go ahead and check and see what that looks like. So Zach, what we got here is we got a series of computers, and again, like I said, their names are kind of arbitrary here, but what I really care about is the MAC address, right? And again, these are just kind of made up on the fly MAC addresses, was still within the same format, right? So client 1 has its MAC address, client 2, right? That's part of an Ethernet-based network. We all have MAC addresses, and remember, that's what the switch is already using to determine where to forward traffic, right? I'm looking at that destination MAC address, comparing it to the MAC table inside of the switch. Well, when you do port security, all you're saying is that on this port that the client 1 is connected to, the only traffic that I'm going to allow into that port is something that's sourced. Right now we're looking at the source of the source MAC address is a MAC address with a source MAC address of this right here, right? 0000122334455, right? Same thing with client 2. If client 2 is connected to the switch, the only inbound communication that we're going to allow on that port is going to be client 2's MAC address, right? Again, inspecting that source and that destination MAC address inside of the Ethernet frame. Same thing here with, likewise with client 3. No different, right? We got a MAC address, and that's all we want to see, again, coming into that port. Right, so we've already got that MAC address there, right, from these computers, and it is in that database, right, and the switch says, okay, I see, and again, just arbitrary port numbers here. Port 2, I see MAC address for client 1. All right, port 10, I see the MAC address. We configure the MAC address port security for client 2. Let's say port 23 has client 03 on it, right? That MAC address is there likewise too. So now what happens? All right, well, it's inspecting those source of the communication as it comes into the switch. And here's what happens. All right, so we got our bad guy, right? And you can tell he's a bad guy by the way he's dressed, right? He's dressed like Frank Sinatra with sunglasses. Apparently, that makes you a bad guy.
An evil Frank Sinatra.
An evil. That's right. That's an evil Frank Sinatra. So what we end up having here is, and I'm sure you're not paying attention to the MAC addresses out there, and that's okay. So let me explain that this MAC address wasn't the MAC address that was actually set in the database, right? So when this switch receives communication on port 2 and it inspects the MAC address, just like it's going to do anyways, and let's fix that. There aren't semicolons there. There we go. It looks at that MAC address and says, let me see who that is. All right, let me look at my database. Yeah, on port 2, I don't see that MAC address. That's not the right MAC address, so what does it do? It doesn't allow the communication. It completely discards it, right? That's part of port security. Now, there are other port security, too, that we could talk about as well, and we'll talk a little bit more in depth later as well, because I don't want to just stop here, but there's also 802.1x, right? That's port-based authentication, right? Switches can actually, and wireless access points, if they're set up in an enterprise mode, what you can do is physically shut the port down as an authentication request comes in, all right? What the switch does is it will pass that authentication through to some kind of authentication server like a Radius server and shut the port down while the Radius server is doing the authentication, verifying that that person should be there, and if the person, or again the device, I keep saying person, if the device should be connected to the network and the authentication is successful, it turns around and it opens the port. So there's a couple different ways you can do it. One of the ways you can do it, port security there, is through kind of like we do with our wireless networks as well, through MAC filtering, right? We can say only the MAC address from this computer can send information into that switch, right? We do it a little bit different for different purposes. On wireless networks, we can say allow or deny, and we can put MAC addresses in a list, right? This is doing it on a port-by-port basis. All right, so those are some of the other interface properties that we need to be aware of. I would say probably the next thing that we should be aware of is what is known as VLANs. All right, what is a VLAN? A VLAN is a virtual local area network. It's a layer 2 technology that allows you to essentially, logically if you will, divide up a switch into more than one switch. See, if I've got 48 ports on a switch, what do I have? I have one big, huge broadcast domain, right? We talked about broadcast domains. Yep. Well, if I want to maybe logically divide some of those ports up, then what I can do is create these logical software, if you will, based local area networks. And let me show you what I mean here. So I've got, just an example of a VLAN that you might see, VLAN diagram, right? So I've got one switch, right? Remember, switches are only aware of what is connected to them, so these computers have to be plugged into the switch. And then what we can do inside of the software in the switch is that we can configure it, and we can logically group these computers together so that only they can communicate. That's why they call it a virtual local area network. That's what a VLAN is. It's a software-defined local area network. Now, don't confuse that with software-defined networking. We'll talk about SDN later, but what this is it's logically defined in software. All right, so that means that PC1, PC4, and 5, they're on their same virtual network, right? And they can't communicate with, if they're on VLAN 10, they cannot communicate with VLAN 20. These servers, I can segment them, I can separate them from the rest of the computers that are on separate VLANs, isolating their communication just for those devices that are within that same virtual local area network. Now, how would we allow these to communicate? Well, that's where you could stack on a router, and then the routing, it treats them like they're their own virtual local area network. Remember, we can't communicate across networks without that layer 3 technology. So this is a way that you can, for security purposes, you can isolate the communication that happens between a group of computers by logically defining what LAN they're in based on the configuration in the switch, right? Another way that you can look at this is that logically through the access control list, like we talked about ACLs, right? We can define that these 10 computers, regardless of their physical location, are now seen to be on the same isolated local area network, hence the term VLAN, where these servers, maybe I only want these servers communicating. Maybe I've got a management station and a server, and I only want them to be able to talk together, and I don't want them to talk with the rest of the PCs within the network, right? So I can put them on their own separate VLAN, and only those communications will stay within those VLANs and only go between those computers. So how is it that we accomplish virtual local area networks, right? Well, you have to have a managed switch, all right? That's important, right? You're not going to do this with one of those little Linksys switches that you just plug in, you turn the power on, you plug the devices in, and you go, right? Those are unmanaged switches. And unmanaged switches, they've got all the logic built into them, and they don't have an interface that you can type in commands, drop down to a terminal, you know, do an SSH into them and start configuring them, right? A managed switch is that one, again, that you can console in, you can SSH into, and you can make configurations in the ACLs, and you can define how or what computers are on what VLANs. Now, how that happens is through a technology known as 802.1q. That is the IEEE's industry-wide standard for VLAN tagging, trunking as well. And we're going to talk about what that means here in a second, all right? There's another protocol, too, that's Cisco proprietary that I don't know if it'll come up on the exam, but InterSwitch Link, ISL, is Cisco's proprietary. They do both. They do ISL and 802.1q. Understand that 802.1q is your VLAN. It defines that VLAN tag, right? And what that means is that in that Ethernet frame, you will see that there is a portion that you are going to actually put a tag on that the switch is going to inspect. And let me show you what I mean here. I like to do this more in like colors, right? So let's say that we've got multiple switches that are in that are all managing these VLANs, right? Well, how do they know which traffic goes to which VLAN, right? When you got a group of switches, well, that's through the process known as tagging. And it just so happens that they'll receive a tagged frame, and again, that'll have that 802.1q VLAN tag. Think of it as like a color, right? And it'll say, okay, this is destined for VLAN 7, all right? And then what it'll do is as it receives, let's say switch 1, we're sending information across VLANs here, the switch will receive the untagged port on an access port, and I'll go a little bit farther with that here in a second, and it'll turn around, it'll look at its table, and through that access control list, it'll say, okay, which VLAN is this supposed to go out on? And it'll say, okay, I see it's VLAN 7, I've identified it, let me go ahead and put my tag on it, and then what I'll do is I'll send it out that interface, and it goes to switch 2. Well, switch 2 receives that, inspects the VLAN tag, and says, all right, I see this is for VLAN 7. Let me go ahead and untag it, and I'll look at my table here and see where I should send this out to get it to VLAN 7, and it'll put the tag on it, and it'll send it to the next switch. Finally, the last switch that maybe is directly connected to where the destination PC is within that VLAN will receive that tag and say, oh, okay, I see this is VLAN 7. Let me go ahead and untag it, and I'll look at my interfaces here that are configured on me, and I'll figure out which way I need to send it out. And at that point, once it's actually on the VLAN, it doesn't need the tag anymore. It knows where to send it, so it's actually going to be an untagged frame at that point because it identifies it as being on that local VPN, or on the VPN. Nope, I didn't change that color. Let's try that one more time. There we go. Try that. All right, so it's actually untagged when it gets to that location. Now, another way we can look at this too, all right, is access ports versus trunk ports, all right? So what do we mean by that, all right? If we look, and we've got a series of computers here, and they're on VLANs, all right? All I did here is I essentially cut out switch 2, all right, if you will. So we just have 2 switches here, just to kind of make the diagram a little bit easier to view here. All right, notice that I've got these 2 switches, and they are managing the VLAN. If I can get that in the picture there. They're managing the VLAN. Now, if this computer, all right, sends information into the switch, all right, when it sends information into the switch, it's in an untagged format. And that untagged format, that's the access ports. That's the difference between, you know, an untagged port versus a port that will do the tagging. See, what happens here is access ports are those ports that deliver the traffic directly to the device. A trunk port is essentially a port that more than one VLAN can use, right? See, we've got multiple VLANs. Well, if this VLAN 7 and VLAN 8 have to send information to this switch to get to VLAN 7 or VLAN 8, they got to be able to share a port, right? And that's what a trunk port is. A trunk port, if you will, is just a port that multiple VLANs can use. And they use that tagging frame, or that tag within the frame, if you will, between the switches to identify what what VLAN it should go to. And then when it gets to this switch receives the tag frame, says, oh, okay, I see, that's bound for VLAN 7. I'm connected to the VLAN that computer's on. I'm also that computer's connected directly to me. So what it does is it removes the tag and it sends that information in an untagged manner out finally to the destination PC. So tagging and untagging, we're just talking about how VLANs operate, how the switches themselves try to determine where to send that information. All right, so that is a little bit about our VLANs, the VLAN tagging. We do have some more to talk about, but unfortunately, it looks like we might have run out of time.
Well, Wes, that'd be great, but you know, we actually do have a couple of more minutes. Is there anything else you'd like to add about switching technologies?
Absolutely. There are a couple other topics that we just kind of need to wrap up here. So we'll go ahead and we won't make you wait. No more cliffhangers in this one, all right? So one of the other things that we want to just briefly mention here, and you need to be aware of for the exam, is that, you know, we talked about some of the properties of our network traffic, and one of those things is broadcast communications. And remember what we said, right? Broadcast communications.
Everybody.
That's right. Yeah, you know, that was like standing up on the table in the food court and yelling out, and everybody looks at you and wonders why you're doing that. But everybody hears it, right? Well, broadcast communications can cause problems, right? Not only do they saturate our networks with unnecessary traffic if only one destination is really needed, but the other problem is that when you have multiple switches that are basically, you know, servicing a larger network, a larger LAN, is that one switch might send a broadcast communication. And I tell you what, let's go ahead and explain. I got a little diagram here. Let's talk about how we can, essentially what happens, a broadcast, if we get too many broadcasts, we can get what's known as a broadcast storm, right? And it causes what's known as switching loops. In order to stop this, we use something known as STP or spanning tree protocol. So I want you to take a scenario, right, where this switch sends a broadcast communication out, right? Remember, we're talking about that all F address, right? And in fact, if we switch back over to our Windows client here, remember, we have a broadcast MAC address, right? That's where we send a broadcast communication to the switch because we need everybody to hear it. Well, the problem with that is, what happens if this switch sends a broadcast communication, right? It is sending a communication out to all the other switches that is destined for all Fs, right? The MAC address all Fs. Well, what happens when this switch receives that broadcast. Well, it says, oh, okay, I see it's a broadcast communication, and then it broadcasts its information or out all its ports, right? And then what happens again? Well, then this switch, it hears it, right? And you can see what's going on, right? This switch hears it and says, oh, that's a broadcast. So what does it do? Well, it sends it out all of its ports. And now what happens? This switch and this switch just received another broadcast communication. Even though it was this switch that started the broadcast communication, this switch will receive it, this switch will receive it, and then we're back to the same thing. Notice that we've got, again, we've got this, it's called a broadcast storm, and it just, those broadcast communication, every switch is receiving a portion of that broadcast communication and saying, oh, well, let me send this out to the broadcast MAC address. And then cycle just, you see what's going on here, the cycle just kind of repeats itself, and pretty soon all of these broadcast communications are just ending up in these loops across our switching technology. So what we do is, with spanning tree algorithm, or spanning tree protocol, it uses an algorithm called STA, spanning tree algorithm. Sorry about the acronyms there, the alphabets too. It gets confusing. STP uses STA. Class dismissed. No. Okay. Spanning tree protocol uses an algorithm called spanning tree in order to do a few things, all right? So I want you to know, all right, it's a loop prevention mechanism at layer 2, right? What it does is the algorithm takes all of these switches, and we can go look at our slide here. All of these switches are going to go through what's known as an election process. And the election process, what it does is it's determining the main switch, right? Who is the king of all the switches, right? That's what becomes the root switch, or root bridge, as they call it. They call it a root bridge because bridging technology, switching technologies are pretty much, they're the same, right? So this goes back from the early days when we had bridges, but they still call it a root bridge, right? Well, what the root bridge is the root bridge is the top part of the tree, right? It's going to start to try to form this tree topology so there aren't any loops, right? And the top part of the tree is called that root bridge. And the root bridge's ports are always in forwarding mode. All their ports are in forwarding mode. Now, the root bridge is determined by priority, and it uses a MAC address, all right? A MAC address and a priority, and by default, all switches have the same priority. So a lot of times what will happen is, if you let spanning tree protocol go, is that it's going to choose the MAC address with the lowest value. That'll be the highest priority. It'll become the root bridge. And there can be problems with that as well, because a lot of times what you have is your oldest switches have the lowest priority or the lowest MAC addresses. And a lot of times your oldest switches are the slowest switches, right? They're the oldest technology. So a lot of your administrators, like in Cisco and stuff, will manually define what the root bridge is. But you can let STP do this as well. Now, once the root bridge has been elected, now we got to go through another process, right? And that's determining which ports are going to actually be forwarding information. So that's another part of this, right? So it determines are loops present. And if loops are present, we got to start blocking ports. So what we're doing here is we're determining which ports will be root ports, and root ports are going to forward information always back to the highest part of the hierarchy, back towards the root bridge. And then you have designated ports which can forward to other switches, not to the root, but to other switches. And then you have non-designated ports, and non-designated ports are those ones that we close down. And what it's trying to do is make sure that it creates this loop-free topology. And then finally what you have, you'll see that the ports, the root ports, right, they're only going in one direction. They're only forwarding traffic to one direction, and that's back to the root, right? So remember, you have root ports, you have designated ports, and you have non-designated ports. Root ports means these are the shortest, this was determined that it's the shortest path back to the root, and the designated ports are forwarding to other switches. So do keep that in mind. Any kind of loop that is detected, those ports will be shut down, and those are non-designated ports. All right, so a little bit about spanning tree algorithm. Again, as you go on to more advanced training, you'll learn how to configure this, and you'll learn it in much greater detail. I would say on the Net Plus exam, know the process that's happening, right? Know that it's a priority and a MAC address that determines the root bridge election. Know that it's root ports, designated ports, and non-designated ports. Essentially, the root ports are that shortest path between that switch and the root bridge, if you will, or the root switch, and then designated ports forward just to that segment, and then last but not least, non-designated ports are blocked. That takes me to one other topic, or I guess we got a couple other topics here, and we will finish up. The next thing I want to talk about is what's known as a DMZ, and you might have heard this in our security section where we talked about a demilitarized zone. There are a couple of different ways that they define this in other technologies, more vendor-specific terms. You might hear screen subnet, perimeter network, edge network, but if we can look here, our DMZ is typically any resource that is publicly accessible from the internet. All right, so I want you to think about this. We don't want people out on the internet being able to connect back into our local area network, right? That'd be a security vulnerability. But what we might have is we might have a web server if we're a company that needs to sell our product, right? Well, we might have a web server where we need customers from the internet to be able to get to. So how do we allow access, public access into that resource without actually allowing them access back into our private network or our LAN? Well, that's where a DMZ comes in, right? A DMZ, a demilitarized zone, essentially is a subnet. It's usually placed in between two firewalls where the external firewall allows communication in. You can communicate with the web server, but it doesn't allow public access back into the local area network, right? So it is basically a network that sits between the public side, public-facing side, which would be the internet, and the private network, which would be your local area network. All right. Last but not least, I say last. It does look like I got two more topics here. I know we're running short on time, but I also want to talk briefly about distributed switching, just so you can understand that, what that means. And again, this is something that you'll see in some of the vendor-specific training as well. And what this does is this actually just breaks up and puts a hierarchical implementation to switching, essentially a hierarchical model with multiple layers. And what you have are these three layers. You have an access layer, a distribution layer, and a core layer. The access layer connects the clients directly to the network, if you will. The distribution network can be things like LAN-based routers, layer 3 switches, and it moves the data, like for instance, across VLANs. The last is the core layer, and the core layer are high-end switches with high-speed cabling like fiber optic communications. Think of it as like the backbone. They're going to handle the traffic from everything, right? So a lot of bandwidth, basically high-speed cabling compromising the backbone of the network. And that's just those abstract, that hierarchical model that they apply to switching. They call it distributed switching. Distributed switching. Not swishing. We're not teaching how to brush your teeth here. That's right. And all right, last but not least, and I'll quit saying that, sound like Columbo episode here, is something known as Power over Ethernet, PoE. All right, PoE is exactly what it sounds like, ladies and gentlemen. It means that we've got Ethernet cables and we inject power onto them so that we can power devices. Now, where do we see this? Where would this come in handy? I want you to think about any kind of like an access point that you can't run an external AC adapter to. Right, an IP camera, right? You have some kind of security camera and you want to be able to send data to it and from it, but you don't have a place to mount an external AC adapter. Well, you can plug your Ethernet cable into it, connect it to a PoE injector. It puts power into the Ethernet cable and powers the device. There are two different PoE technologies that I want you to be aware of for the exam, right? There's PoE and PoE+. PoE is 802.3AF, right? Alpha Foxtrot there. PoE Plus is 802.AT, Alpha Tango, all right? So what's the difference between these two? Basically the output of wattage, right? One's got a higher wattage output. The first PoE, or 802.3F, that would, 802.3AF, let me make sure I say that right, would give you 15.4 watts. If you're talking about PoE Plus, it increased the wattage output up to about 25.5 watts. So PoE Plus, or 802.AT, is going to be 25.5 watt output. So just more of those specifications that you have to know for your Net Plus exam. Remember some of these technologies, remember some of the fundamentals, and you'll be doing well the next time you sit in that exam booth.
Awesome job, Wes. Another essential episode, switching technologies. And that's part of the compTIA Net Plus series. Make sure you see every single one of them. And that will be in the course library, where you'll find hundreds of other videos, all designed to help you go so much further. And tell everyone you know about IT Pro TV. It is binge-worthy. Thank you for watching. I'm Zach Memis.
And I'm Wes Bryan.
And we'll see you soon.
Thank you for watching IT Pro TV.